Hi everyone, welcome back. Happy Wednesday. We left off last time just starting to crack into OFDM in this OFDM module. And because of that weird timing, I've asked you to watch videos on something before I've really introduced it. But I think that our lectures should catch up with the external video lectures, and we should be able to wrap up today with a bit of a Q&A, and maybe even some small group work to try and deepen our understanding of what's going on. So before I switch over to the PowerPoints, any preliminary questions? I do promise to give you time to ask questions at the end of class as well. Okay, so let's go back to this slide 16 in my set. And the big picture was as an alternative to equalization. And again, equalization is the idea to try and undo whatever the channel does, including delaying and echoes and noise addition. What if, instead of requiring that all of our data symbols get transmitted as soon as we get them, what if we just chilled for a little bit, and that little bit, it makes sense to wait only the length, I should say, of your channel's impulse response. Because if you wait any longer, then everything that you've sent has already died away, and so you're using dead air at that point. And anything shorter would mean that you are still hearing echoes of symbols past. So the idea is don't send a symbol every time you can, but rather send a chunk of symbols and then wait until they clear out of the channel, if you like. So that's called using guard intervals. So in the time domain, instead of guard bands in the frequency domain, they're guard intervals in the time domain. So send some symbols, wait a bit, send some more symbols, wait a bit. And so chunking up those symbols, those are called frames. And so in the wait a bit, you could either send 0, and that's fine. That is a way to not send anything through the channel. But what we'll see is that you can also send what's called a cyclic prefix. So rather than sending zeros, send a cyclically shifted version of your signal such that, and the goal behind cyclic prefixing is, one, it actually works better with our DFT that we're going to use, and two, it has the effect of reducing the chance of this steep or sharp change between whatever x3 was and a 0 signal, because but the change on average between x3 and x0 tends to be less, so you get fewer discontinuities, which means you get fewer or less bandwidth spread. Okay, so let's see how this would work using the 0 padding. And so we're gonna actually not treat the noise. The noise is going to be what it's going to be, and the noise doesn't care if we're waiting or not. So I'm actually just looking at the signal, and we're kind of letting the noise fall by the wayside. And so the demo is just going to be a simple two-tap channel. So this is L equals 1, right? Because we're saying that the H of 0, H of 1, and then we're calling this L. So this is the channel impulse response. And I think that we're going to do a frame of 3 data bits. So, 3 data symbols, followed by, so x0, x1, x2. And then if we have an L of 1, then we would then send a single 0. And then we would have x3, x4, x5, and then another single 0. So the L equals 1 tells us how many zeros to put in. And the frame length is a little bit arbitrary at this point. Mainly, I just picked 3 to make it computationally feasible. But you can imagine that if the frame length were very, very long, then we actually wouldn't notice the loss, right? If the total length of a frame is n, then you could say something like the data efficiency would be n minus L over n. That's how many data symbols you're sending per symbol slot. And as n gets large for fixed L, this goes to 1. Okay, so this is not the case. This is pretty low efficiency in our little toy example here. Anyone have an idea as what? So why not just let big N go to infinity? Like that seems like the mathematical thing to do. Any thoughts on why that might not work?
Doesn't that defeat the purpose of removing the ISI?
Yeah, you could say that, because the whole idea is that you give the channel time to relax. But I mean, we're still saying, like, even let n be 1,000,000, and then if the channel is a 2-tap channel, then we just wait for 1 symbol time and we start the next 1,000,000.
Would it just be not very efficient if you're sending, 3 data symbols over this many n time? It's not very efficient when you could send a lot more over the same t.
Yeah, so that's the draw. That's the draw of letting n be large relative to L. But I'm saying that there has to be a price to be paid for that.
Wouldn't your impulse response just be super, super long then?
Well, the impulse response of the channel is fixed at length 2. Now the response of, say, 1,000,001 symbols would be then 1,000,001 long. Let's see here, who's chatting? Small compared to number of data symbols. Sorry, Jack, I don't quite follow what you're saying in the chat box. So maybe this wasn't, it appears that it's not obvious. Never mind, I think I asked an answer to a different question. Okay, fair enough. So what we're going to end up doing is having to unpack all of these symbols out of this array, right? Because they are going to be corrupted by noise, and we're going to have to do maybe even an equalization to get rid of the 2 length channel interference. And so what we'll end up having to do is doing our equalization on these frames 1 frame at a time. And so if your frame is 1,000,000 symbols long and your symbol rate is, I don't know, 1 megasymbol per second, then you are only going to get data out of your receiver once every second. You're going to get 1,000,000 symbols every second, but it's going to be a very kind of halting process, if that makes sense. 1,000,000, wait for some number of milliseconds, and then another 1,000,000, wait for another milliseconds, then another 1,000,000, rather than a more continuous stream of data. This can be overcome if you have a buffer, right? So then the output of your receiver gets put into the buffer, and then the buffer kind of trickles it out at a regular rate. But the longer your frame is, the longer your buffer needs to be, the more memory you need in your receiver. Okay, so that's one of the arguments against just letting your frame size grow and grow and grow, is because we'd like to get the symbols in and out of the channel and then to their receiver destination in a somewhat steady process. Okay, so that was actually all kind of an aside. But let's work out what the received symbols would be, given, so remember X are the transmitted symbols, transmit symbols, and then the channel impulse response, and then these are the received symbols. Which technically, I don't even know if you want to call them symbols, because they won't be constellation points. They'll be something on your IQ plane. But just be careful about calling these symbols. They would have the same units as symbols, but they wouldn't actually line up to your constellation. Okay, so this is basically an exercise in viewing discrete time convolution as matrix math, right? So this is your discrete time convolution at 3 different time instances. These are your n's. And so all we're doing here is we're changing these n's to match the n's on the left-hand side, and then recognizing that this pairwise product and then sum is the same as an inner product or a dot product between vectors. Now here is actually the special sauce, because normally this would be referring to x of 0 minus 1, so it'd be x of negative 1. But in our string of symbols, there we go, there is a 0 there, right? So this 0, it corresponds to that 0, our 0 padded from the previous frame, if you like. Okay, so if I can write these individually as matrix multiplications, there's nothing stopping me from stacking the z's in a column and then saying that 0, x0, x1, x2 are in their own column. And let's play fill in the matrix here. So z0 needs an h1 times a 0 and an h0 times x0, and then zeros on these guys. Are you following my, this vector falls on top of this matrix and we get h1 times 0, h0 times x0. So I think we are doing these 2 multiplications and then nothing else. That's the 2 zeros here. Okay, and then actually, yeah, do you wanna fill in the second row? Can you predict what's gonna happen here?
Would H0 on the second row go below the first row's H0, and then H1 would go on the third one? No. Yeah. So H0 would go on row 2, column 2, and H1 would go on row 2, column 3.
Okay. So let's make sure I got that right. So this is h of 0 times x of 1 minus 0. So that's, yeah, h. Oh, this is the problem. I thought this looked funky. There is a typo on the slides, which is not helpful. So let's write this out. This is h0 times x of 1 minus 0 plus h1 times x of 1 minus 1. So this should be h of 0 times x of 1. I think we need to flip these guys around. So typo. And then just to be sure, if I made that typo there, I likely made it down here as well. This is h0, so let I be 0, times x of 2, plus I is 1, so h of 1, x of 2 minus 1, so that's 1. Okay, so yeah, again, typo here as well. Okay, so with that in mind, we want now h1 to be acting on x0, and we want h0 to be acting on x1. So there we go. That's the pattern that I wanted to emerge out of here. I wanted a cyclic permutation. I want a cyclic shift. So down and right, down and right, down and right, down and right. Okay, so if you were going to be building an equalizer to try and undo the channel effects, something that you might consider would be trying to invert this matrix. Call it, well, I mean, it's just filled with channel tap values, so maybe just call it H. Can you invert H? Right, I have the Z's, and if I had the H, could I invert the H to get me the X's back again?
Could you not, because it's a square matrix? It's not a square matrix?
There we go. Yeah, you cannot invert this matrix because it's not square. This is a 4 vector. This is a 3 vector. So we're transforming a 4 vector into a 3 vector. So kind of compressing space, which then means to undo that, we'd have to expand space. And so that's a tricky proposition. You can't do it with a true matrix inverse. What you can do, and I actually don't know if they teach you this in your linear algebra class, is what's called a pseudo-inverse. Have you ever heard of that term? All right, well, we get to learn something today. The pseudo-inverse is a well-defined operation for matrices of any size. And it's what you can do if you would like to do something that an inversion would help you with, but your matrix isn't square or your matrix is singular. Pseudo-inverse is, there are a couple different symbols for it, but I like the plus sign. If you're trying to Google this, this is technically called the Moore-Penrose pseudo-inverse. And the idea is that the Moore-Penrose pseudo-inverse will give you the best estimate of the domain vector in terms of the minimum mean squared error. So here's that minimum mean squared error coming back again. So if we do something like H pseudo-inverse times H, we are not going to get the identity matrix times the X vector is H pseudo-inverse times the Z vector. But what we will get is we'll get something on the left-hand side that has, in some sense, the minimum mean squared error between the result here and the X vector over here. So this, call it Z hat. Z hat minimizes amongst all Z's, X minus Z, in some sense, it minimizes the mean square of the difference. Okay, so it gives you, in some sense, the closest you could guess in a space of, so given only 3 data points, or given data in a 3 space, it's your best guess about what 4 space vector would map to that 3 space given H. All right. So, and that it's doable. It's actually, it's fairly speedy to do this numerically. It mostly relies, or most algorithms rely on something called the singular value decomposition to determine the pseudo-inverse of a matrix. And so we're getting kind of far afield from communications. We're getting pretty deep into linear algebra, but it's once you get past a certain point, it's kind of hard to differentiate the two. But anyway, I think I'm losing the trail.
Remembering correctly or not, but is the pseudo-inverse only limited to like the positive triangle matrix?
What's a positive triangle matrix?
Like when it has the diagonal values and then it can only have it like on the upper side, not the lower triangle? Like all the lower triangle is all zeros? Is that one of the conditions or no?
I don't think so. In my experience, you can find the pseudo-inverse of any Any matrix.
Oh, okay.
Your estimate is gonna be only as good as kind of how far your matrix is from invertibility, true invertibility. So yeah, I'm not familiar with that restriction. Okay, so this is what one would do if when we're going to zero pad for your guard intervals. Alternatively, if you cyclic prefix, so now the setup is still got 2 taps, so same channel, let's say, and now we're sending x0 and then x1 and then x2, but, and this is the idea behind prefix, you have to wait until the x2 comes around before you send this quartet, okay? And then the next would be wait a bit, and then you x3, x4, x5, and then populate that with x5. Okay. So same idea with zero padding, except you have to wait for your last symbol, data symbol, before you can pre-populate that and send this frame over the air. Okay, so now this x sub -1 is well defined. It's now x2. And so if I am consistent, then I've also made the same typos on this slide as the last slide. Double check. Yep. Okay, so it helps to be consistently wrong. And then now let's double check this one. So this is h0 times x0. Yeah, that works. And then plus h1 x -1. Yep, okay, so I got the first one right, but none of the other ones. So now what would this look like stacked in a matrix? So this would be z0, z1, z2. And now, well, x0, x1, x2. So here's the trick. Did you see what just happened? This is now a 3 vector. Because in order to write the first row, I put an h0 here, and I can put the h1 over there, rather than going behind it, and a 0 in the middle. And then we permute again. So the h1 now multiplies the x0, and h0 moves down, 0 moves down, and then we permute again. So now the 0 bumps around h1, h0. So overall, we're still doing cyclic permutation. So this one then goes around and comes here. The cool thing about doing cyclic prefixing is that we get to invert this matrix. So this, call it H cyclic. This is going to be square, simply because we're doing a 3 space to a 3 space. And so what you'd like to do at your receiver is, so remember, we're getting these Z's coming in from the channel. And what would be really nice is we could do some kind of H cyclic inverse on them. And what comes out isn't going to be X's, they're going to be X hats because of the noise that we've been ignoring for this entire lecture. But at least now we can imagine, in the absence of noise, that this would be perfect, right? If Z had no noise component inside of it, then we could invert this H matrix and we'd be good to go. Does anyone, this is a long shot, and I know this is the second long shot I've taken on linear algebra in this lecture, but does anyone know the nice properties about circulant matrices in terms of their eigenvalues? So yeah, this is called, whenever you have a matrix whose rows are cyclic permutations of each other, this is called a circulant matrix. And one property of circulant matrices is that their eigenvalues are exactly the elements of any given row. So that is, if you have, so that actually gives us a little bit of an issue here because of our invert here. So this would have a 0 eigenvalue, which would make this inversion process, this matrix inversion process, problematic. But I think that's one of the cool things, is that if you have these eigenvalues that are given by your, oh, so sorry, that's not actually true. The eigenvalues are the Z transform of the rows. That's it. So what this means is that you can always write H cyclic as a unitary matrix times a matrix of eigenvalues, diagonal matrix of eigenvalues, times another unitary matrix. So this lambda matrix is diagonal with eigenvalues on that diagonal. And then these U matrices are matrices of eigenvectors. So these circulant matrices have really nice what we call spectral properties. Whenever you're talking about eigenvalues, eigenvectors of a matrix, linear algebra people call those spectral properties. So if you know the spectral decomposition of this matrix, then you can invert it actually really quickly, because to inverse this matrix, well, what would you have to do? What we want is H cyclic times H cyclic inverse. That would be identity. But we know that H cyclic is, if I multiply both sides by U and U dagger on either side, so multiply by U dagger, that means I multiply on the left by U and on the right by U dagger. And then I'm left with this, a unitary matrix times its own conjugate transpose is identity. A unitary matrix times its own conjugate transpose is identity, which means that I'm left with a diagonal matrix on the right. And so if I multiply both sides by the diagonal matrix whose entries are the reciprocals of the diagonal entries of lambda, then I can get identity. So then I get U times H cyclic times U conjugate transpose times a matrix 1 over lambda 1, 1 over lambda 2, all the way to 1 over lambda n. That will give me identity here, which means that this is H cyclic inverse. So if you knew the eigenvectors and you knew the eigenvalues, then this is a really quick way to invert your circulant matrix. Okay. Everyone having fun? The reason that this leads into OFDM, so I promise we're getting there, is that if you think about that circulant matrix property, where did you last see a circulant matrix? It was likely in 328, when you were talking about DFTs. So this is an alternative way to approach OFDM, as from the video that you watched. But if you're doing circulant matrix type arithmetic, then doing FFTs along with that should play well. So the idea is that instead of sending the symbols themselves, we are, and that's why we kind of have this trivial mapping. So in this slide, I kind of had these arrows that mapped symbols to x's, and I suspect you were wondering, why did I switch from s's to x's? And I'm going to give you the answer to that, and that's because in OFDM, you don't actually send the symbols, you send things that are functions of the symbols. And that function is an inverse fast Fourier transform. So let's get the whole picture here. So let's say we've got a symbol stream. S sub k or S sub n, whatever you like. And this also means that these symbols have to be digitally like modulated first, right? So what has to happen upstream? Well, upstream we have to do something like BPSK or QPSK or 16 quam or something to map our bits to our symbols, right? So, but I'm just kind of picking it up after we've done that modulation. And then if those symbols are coming in serially, then we need to do buffer operations, serial to parallel. And then what we're going to do is we're going to pass that column vector, if you like, into an inverse FFT operation, which means that somewhere along here, we need to chunk or block or frame our data, right? Otherwise, this IFFT only works on a finite number of samples. So we need to somehow divide this stream up into only those samples. And so yeah, if you like, the serial to parallel can do that as well. You fill this register until it's full, and then you pass that entire register on to the IFFT. And then you start filling the register again. Okay, so then once we've got these, which I've been calling X vectors, now we go through a cyclic prefixing, which is going to extend the length of this X vector by L positions. And then we are going to take that vector, and actually, technically this does go back through another parallel to serial, because then we mix that up, mix to passband. Send it through whatever channel you're going to send it through, and then take the received signal, mix it back down to baseband. You've got this string of waveforms coming in, and so now what you need to do is take this series and parallelize them again. Take off the cyclic prefix, and then you're left with things that should be inverse FFTs of the thing you want, which means what you have to do is take the FFT of that. Right, everything on the receive side should be the opposite of what you were doing on the transmit side. Then you've got a parallel vector, so we'll need to serialize that again. and we're left with SK hats, so things that should be close to our old symbols. If you like, you can introduce a delay in there, so this might be SK delayed by U. But this is I hope this is built upon our development so far. Like everything in here has a purpose. The chunking or the blocking is to try to give ourselves some time to put the cyclic prefix in. The FFT and IFFT, there are a couple explanations for that. So my explanation so far, and I admit it was a pretty weak one, is that we're doing circulant stuff anyway, so we might as well do DFT. I think the better explanation came in those videos, is that if you're doing FFT and IFFTs, you are necessarily doing orthogonal modulation, because everything in an IFT or in a DFT, let's see here if I have the formula. There we go. So doing an inverse DFT, this is something like the nth sample is the sum over a bunch of frequency domain objects, capital X sub k, times e to the positive, j 2 pi k n divided by the frame length n. And so the orthogonal in OFDM comes from the fact that these basis functions are orthogonal. And so if we do our DFT or IDFT over a symmetric range about the origin, then what you're seeing here, if you apply Euler's formula, is a whole bunch of cosines or sines. Right? So if we take pairs like plus minus 1, plus minus 2, plus minus 3, pairs of k, then we're getting x plus or minus 1 times e to the j 2 pi n over n times plus or minus 1. And this is going to be a cosine. Okay. Or a sine, I guess, technically, depending on the SIGN of this guy. And the idea is that they are all orthogonal because they are going to be, see this little n here? They're going to be harmonics of a fundamental. And the fundamental is 1 over n. Or sorry, 2 pi over n. So the upshot of all this is that, I guess, I don't know, I should pause here because I promised you I would give you time to ask questions about the videos. And so I think this is I could talk some more, but I actually want to be sure that I give you time to ask the questions you want to ask. So go right ahead.
I was wondering, because in the video he showed that, I'm assuming when he said UE, when he was explaining subframes and resource blocks, he meant different mobile devices.
Yeah, exactly. So UE stands for user equipment in telecom speak. Yeah.
Gotcha. So when he showed it, he was showing it that if you go up the frequency, that's FDD, and then down the time axis, that's TDD. But I thought for different LTE bands, they're designated as either FDD or TDD, not both.
Yeah, so they wouldn't be both. And I think that he mentioned that a little bit in the very beginning, where he said that in Europe they do one, and then in India they do the other. But yeah, the idea is that you would like, so this TDD and FDD are talking about duplexing between, say, a mobile phone and a base station. And the idea is that either the base station talks on one lower, higher frequency downlink, and then at the lower frequency, the mobile transmits simultaneously on those two parallel channels, or you can alternate between downlink for this time and then uplink for the next time. But I don't think you could do, unless you had a different kind of duplexing, I don't think you could do both simultaneously.
Gotcha.
I had a question regarding the IFFT and the FFT blocks.
Sure.
Because I remember towards the beginning of the slides, what we mentioned that one of the, I guess, like disadvantages of like regular FDM is that you'd have all of these like local oscillators that would be very costly to have to actually implement.
Sure.
So are these IFFT and FFT blocks supposed to, is that where like OFDM kind of takes care of that disadvantage from regular FDM?
Absolutely. Yeah, and so it's actually, I think he might have mentioned this in the videos as well, like the concept of OFDM isn't new. Everyone. People who have thought about this have wanted to put their data on orthogonal subchannels for as long as we've had amplitude modulation, basically. But exactly the point is, up until recently, the only way to do that was by physically mixing at each of the channels, which, as you mentioned, is going to be costly both in terms of power and money and space. It was only within the last, 20 years that the ability of a microcomputer to compute the FFT, and that's why it's called the fast Fourier transform, to compute the FFT in a small enough time has exceeded the data rates that we want. Right? So in order to do this, you need to be able to do an FFT and reverse it within, n times your symbol rate. And so data rates kept inching up higher, and FFT speeds didn't catch up until the 90s, basically. So that's why OFDM only started being implemented recently. It's because the ability of microcontrollers to perform FFTs fast enough actually exceeded the rates at which data needed to be transmitted. And yeah, when I first learned this, because you learn FFT, or you learn DFT, and then you learn the inverse. You learn the Fourier transform, then you learn the inverse. You learn Laplace, and you learn the inverse. And so this bothered me that we do the inverse FFT before we do the forward FFT. But if you think about it in terms of, oh, I need these to be time signals, because guess what? I actually have to do time domain things to them. I have to send them in real time. Then it makes sense that if I want time on the right, then I need, not time on the left. So there's no reason to not assume that these SKs are DFT samples of some signal. What signal? This signal. There was a question on Piazza about peak to average power and why that's a thing. Or here, rather than me paraphrase, I should just read it. One of the disadvantages of OFDM is high peak to hour power ratio. If the OFDM symbol duration is relatively long, and this is the other kind of undervalued or the other advantage of OFDM is that it allows us to diminish our overall symbol rate by allowing an OFDM symbol to last in the channel for relatively long, right? Because we are, if the frame is n symbol times long, then this, so for every chunk that we have here, this is going to be n times ts long in terms of the time that it takes to get through this, this duration. Rather than sending every symbol every ts, we're sending n symbols over nts. And so the idea is you take a bit of a zoom out on your data rate and say that we're sending one OFDM symbol, which again, an OFDM symbol is this guy, which is an array of what we would call symbols. Every nts seconds, which means the longer your frame is, the longer the OFDM symbol is given to pass through the channel. And that's a good thing, because if you have a relatively stationary channel, then you're going to have a relatively fixed number of delay taps, right? So if my channel has 4 or 5 taps, then if I can send something through here that lasts many more taps, then I can recover from any kind of smearing, right? The smearing will only occur in a range of 4 or 5 taps, right? These 4 or 5 will be smeared. These 4 or 5 will be smeared. These 4 or 5 will be smeared. And the smearing is somewhat localized. It's localized to windows of size, however long the channel length is. And so if you can extend your frame over many multiples of the length of time that the channel acts, you are inherently localizing your intersymbol interference and therefore minimizing it. So actually, I don't know if I answered the question. It was about peak to average power ratio and long symbol time. And yeah, so long symbol time, I went off on a tangent. But if you think about, if you've got a whole bunch of cosines that you're adding together, if you were to only look at those cosines for a short amount of time, the odds that they would all constructively interfere within that short amount of time is actually quite low, right? Because they will only constructively interfere if they're all in phase once every slowest period. But if you look at the sum of cosines over many periods, then you're going to get behavior like periodic constructive interference. You're frequently going to get destructive interference because the cosines are going to be wiggling at different rates and they're going to be adding and subtracting from each other. But the longer you look at sums of cosines, the more chances you're giving them to constructively interfere. I think that's a reasonable way to look at it. And so this peak to average is the problem with OFDM classically.
You were saying earlier how we don't want to have like a super long amount of taps, but the more taps you have, then that duration would be extended for longer, right?
Yeah, for sure. There are lots of good things about having long frames. But one of the bad things is that your FFT needs to be able to act on a frame length of however long you pick. And so the longer your frame is, the longer your FFT has to run, which means you're eventually going to run into constraints on physically computing that in time for the next data symbol to come through. But yeah, there are lots of motivations for why we would want to extend, make n as big as possible. Did that answer your question?
Yeah.
Okay. Yeah, if you have more questions, please keep posting to Piazza. I will post the problem set from the last module today, so it'll be due a week from today. And I will post the problem set from this module later. I think I'm getting a bit behind, and me putting things off is not helping things. But yeah, look for module 4. So that was line coding. Those problems have been up for a while, but they're going to be due a week from today. And then look for problems from module 5, which was equalization and OFDM. They'll be due a week from whenever they're posted. Okay. On Friday, we are going to start talking about a technology that preceded OFDM, but we're going to talk about it in the opposite order of how it came historically, because I really liked how we went from line coding to FDM to equalization to OFDM. It just flowed a little bit better in my mind. So we're going to talk about spread spectrum, which is actually the complete opposite end of this technology, which the idea behind OFDM is we're putting things in narrow bands and they're living there and they're not interfering. Spread spectrum says, no, spread it out over everything and then reconstitute it the other side. So it's kind of a 180 from what we've been talking about, but it is what it is. Okay, I'll hang out if anyone has questions, but I think class time is over. Thank you.